So what you are seeing, hope I am audible. What you are seeing here is some types of transmission line. So what are the types, can you tell, and what are the applications of coaxial cable? The first one. So the first one is coaxial cable. What are the applications? It is used in television receiver for connecting the television sets to the dish antenna, and in regular laboratory experiments, also in Ethernet. So coaxial cable we use for this television sets to connect antenna with TV, and also in laboratories to do all the experiments we use coaxial cable. And second, we have two-wire transmission line. What is the use of two-wire transmission line? In power transmission cable, this type of transmission line, low frequency we use. Then we have a planar transmission line, or a parallel plate, you can say, parallel plate or planar transmission line. We have two conductors separated by a dielectric. So planar transmission line. The other planar transmission line which is most commonly used is microstrip line. So it is shown in this figure here. So what are the applications of planar transmission line? It may be a strip line, microstrip line, suspended microstrip. So what are the applications of planar transmission line? So this microstrip line or planar transmission line, so these are used at high frequency to design microwave, millimeter wave RF components. So microwave and millimeter wave radio frequency components and devices, we use microstrip line. So like to make a branch line coupler, to make a Wilkinson power divider, to design a band pass filter which can work at microwave frequency, to design an attenuator, to design a circulator in planar form, to design a low noise amplifier which will work at microwave frequency. In microstrip technology, you can design a low noise amplifier, to design a mixer, to design a phase shifter, to design an oscillator, to design an antenna, phase array antenna, MIMO antenna. So you can use this microstrip technology, microstrip transmission line can be used. Am I audible to you?
Yes, sir, you're audible, sir.
Okay, good.
Sir, you didn't start the recording.
Okay, good. So these are the some types of transmission line which we can use at high frequency applications. Okay, for high frequency. Now the question is how to do the study of transmission line, which could be coaxial transmission line or two parallel wire transmission line, or even microstrip line. How to do the analysis? Okay, so microstrip line we will consider separately. Okay, first we will consider two conductor transmission line at high frequency, at radio frequency. So if we consider the coaxial line, the first one, coaxial transmission line. So suppose this line is connected with a source and to a load. So in between the source and load, we are using coaxial transmission line, coaxial line. So how the electric and magnetic field at high frequency? So what will be the electric and magnetic field direction? Now these are vector quantities. So what will be the direction of electric and magnetic field? And in which direction the energy will propagate from the source to the load? So how it will propagate?
Electric field will go through the central lines actually.
So where will be the electric field?
To the central.
Suppose the central conductor in the coaxial line, suppose it is given plus V voltage and the outer conductor is grounded. Now you tell. So what will be the direction of electric field? Yes. if you apply some V voltage, source voltage V to the inner conductor and the outer conductor is grounded,
Oh,
what will be the electric and magnetic field direction? So if we apply some plus V voltage to the inner conductor, so the potential of the inner conductor is positive with respect to the outer conductor which is grounded. So what will be the direction of electric field? Plus charge to minus charge in the parallel plate capacitor, if you remember. So basically the electric field will be from this plus to minus. So it will be like this, radially outward. It will be radially outward direction. So it is shown here. It is shown here. Yes, here it is. This situation. So we are applying plus V voltage. This is source voltage, generator voltage, and here it is load. So this inner conductor is having a positive or higher potential than the outer conductor, which is grounded. Outer conductor is grounded. Okay. So electric field will be radially outward. So the direction of electric field will be radially outward like this. Okay. And what will be the, from the Ampere's law, what will be the direction of magnetic field at high frequency? So what will be the direction of magnetic field? Electric field is in this direction, radially outward, plus to minus. Okay. What will be the direction of this is inner conductor and this is outer conductor? So what will be the direction of magnetic field?
circular.
So from the, from the Ampere's law. So what is Ampere's law? Do you know the four Maxwell's law, Maxwell's equations, Maxwell's law? So that if you know, that is good, or we will discuss later all the four equations. So what is Ampere's law, that you can tell? What is Ampere's law? All are silent. What is Ampere's law? Del cross E is equal to what is Gauss law? Can you tell what is Gauss law? So you forgot. Okay, what is the Maxwell four equation? Del dot D is equal to rho. Del dot B is equal to 0. Del cross E is equal to minus del V by del T. And one more thing. Del cross H is equal to J plus del D by del T. So the del cross H, okay. So the magnetic field H will be, so what will be the direction? The direction will be, it will encircle, the H field encircles the current carrying conductor. So it will be from the Ampere slide will be like this, in circular direction. So this is also vector. So now in which direction the energy will propagate or power will propagate? Pointing vector, Poynting's theorem, Poynting power. So in which direction electric and magnetic field is shown here. So in which direction the energy will propagate, electromagnetic energy?
Into the paper, sir. Z direction.
So it will propagate in Z direction because the Poynting's vector is given as E cross H. E cross H is equal to PE, Poynting vector. So it is, that we will discuss what is Poynting vector. See here, Poynting vector E cross H. So it will point along the transmission. Okay, Z direction. So this was the qualitative analysis. So you are seeing that magnetic field is perpendicular to the electric field and the electromagnetic energy is perpendicular to both the electric and magnetic field. So that means transverse electromagnetic wave is propagating. So what is transverse electromagnetic wave? In the case of this coaxial K line we are discussing, transverse electro EM wave. So what is transverse EM wave, same wave which is propagating here in coaxial line? Coaxial transmission line. So the name is transverse electromagnetic wave. That means electric and magnetic field. So they do not have any component in the longitudinal direction. So that means Ez is equal to 0 and Hz is also equal to 0. In the longitudinal direction, the electric and magnetic field is 0. So for same wave, Ez is equal to 0, Hz is also equal to 0. So we have only transverse component. So the name is transverse electromagnetic. Okay. So that is good, but for transverse electromagnetic wave, how we express voltage and current in terms of electric and magnetic field? Can we express voltage and current along the transmission line or current flowing into the transmission line? So in terms of electric and magnetic field. So when we have closed the switch, so a disturbance is created, and that disturbance is in the form of transverse electromagnetic wave. And because of that, electromagnetic power is or energy is transmitted through the transmission line. So now the thing is, can we express voltage and current in terms of electric and magnetic field or TEM wave? Because we have two methods to do the analysis at high frequency. The first is circuit theory, electrical circuit theory that you know. Other is field theory, electromagnetic field theory. So if the transverse electromagnetic wave is propagating, we do not have longitudinal components of electric and magnetic field. So along the direction of wave travel, the electric and magnetic field is 0. Okay. So then we can express electric and magnetic field in terms of voltage. So voltage and current can be expressed in terms of electric and magnetic field. So V is equal to minus integral E dot dl. And I is equal to, so closed integral S dot dl. So it is written here. From where it is written? Yes, here it is written. So V is equal to minus integral E dot dl and I is equal to closed contour integral S dot d. So now again the question is that what will be the, if we are using the electrical circuit theory or in terms of voltage, so line, so what will be the equivalent circuit of the transmission line? That is the question. So already we had done for low frequency power lines we did. So what was the equivalent circuit if you remember in terms of primary constant R, L, G and C, resistance, series resistance per unit line length, and L was the series inductance per unit line length, G was the shunt leakage conductance per unit line length, and C was the shunt capacitance per unit line length. That you know. So okay. And this RLG and C, this is also the coaxial transmission line, that coaxial transmission line, two-wire transmission line, and for the planar transmission line that you are seeing in this figure, coaxial line, two-wire line, and for planar line. So this is also RLG and C for this type of line is also given. So you can ask how to calculate this. So Laplace and Poisson's equation can be used for calculating this thing. So if that is, if you know that already, then okay. Otherwise, if it is in syllabus, I will discuss. For the line, how to calculate R, L, G, and C. It is given in this table at high frequency, distributed line parameters at high frequency. Second line, this is R, L, G, and C. See here, ohms per meter. It is the series resistance per unit line length. Similarly, Henry per meter, Siemens per meter, and farad per meter. So what is this conductance? So this conductance is because of what? We have here transmission line. So why we have that leakage, shunt leakage conductance? Yes. What is your opinion? Why we have shunt leakage conductance? So here what you are seeing in coaxial line or two-wire line, that we have two conductors. We have two conductors, and in between two conductors we have a dielectric. We have a dielectric. So the conductor is how we can characterize the conductor? How we can characterize? What is the conductivity of the conductor? What is the permittivity of the conductor, and what is the permeability of the sigma C for the conductor? Sigma C is the conductivity, and mu C is the permeability, and epsilon C is equal to epsilon naught is the permittivity for the conductor. What about the dielectric, which is in between the two conductors? Here dielectric, here dielectric, dielectric. So between two conductors we have dielectric. So what is the dielectric? How we can characterize the dielectric material? Again we have what is the conductivity of the dielectric? So you can say, okay, that is sigma dielectric or sigma whatever. So if it is a perfect dielectric, then it will be G. If it is a lossless dielectric, then sigma dielectric will be 0. Okay? And if it is a lossy dielectric, then sigma is not. And then permittivity and permeability of the dielectric material. So mu and mu dielectric and epsilon dielectric. So if it is a free space in between the two conductors, then mu is equal to mu naught, epsilon is equal to epsilon naught. Sigma will be equal to 0. Okay, so this was so that shunt leakage conductance is because of the dielectric conductivity of the dielectric. Say because of that sigma dielectric. If it is lossy, then G is not dielectric. Then G will be equal to G. And if it is a perfect conductor, then what will happen? Sigma is infinity. Then what will happen? For the lossless transmission line, R is equal to 0. The resistance will be 0 if it is lossless, and G will be also equal to 0 if it is a lossless transmission line. We will see. So first we have to derive the design equations. We have to derive the equations for the transmission line. Voltage and current expression we have to calculate. Okay. So how to calculate? Already you have done at low frequency. So at high frequency, how to calculate the voltage? How to calculate that? So the equivalent circuit is shown here. So we will consider delta Z length of basically a small section of a we will. Here it is this type of equivalent circuit you already know. So in terms of RL, G and C, so it is indicated here G and C shunt conductance and shunt capacitance, series resistance and series inductance. Okay, so AL type we can consider the equivalent circuit. Okay, delta Z section for delta Z section. So for the delta Z length of a transmission line, so this is the L type equivalent circuit model. Already you have done this. So L type equivalent circuit model is the for a delta Z line length, infinitesimally small line length. So what you are seeing here? What you are seeing here? We have R delta Z series resistance, because R is the series resistance per unit line length. Okay. So for delta Z length of the transmission line, what will be the series resistance? R into delta Z. Similarly, what will be the series inductance? L into delta Z, and conductance G into delta Z, and shunt capacitance C into delta Z. Delta Z length of the line. And here the generator voltage. So here we have generator in this. Okay, here in this direction generator, and here we will connect a load. Okay, so generator is connected here and load is connected. So the voltage is V, Z, comma T. Voltage is a function of Z and T. Okay, because voltage and current we can write in terms of electric and magnetic field uniquely related. Voltage and current with electric and magnetic. Basically, note the EM wave field. So okay, so here VZT at this point Z, and since the line length is delta Z, it is Z here. This is Z plus delta Z. So the length is delta Z. So at Z plus delta Z section, so here V, the voltage is V, Z plus delta Z and T. Okay. VZT and VZ plus delta Z, comma T. And current, here current is IZT and here current is IZ plus delta Z, comma T. So now we have to apply the Kirchhoff's voltage law. So first apply Kirchhoff's voltage law, then we'll apply Kirchhoff's current law. So what will be Kirchhoff's voltage law? Yes, what will be Kirchhoff's voltage law? Applying KVL. So we will apply KVL here. Transmission line. So what will be the as per the Kirchhoff's voltage law? So this VZT will be equal to VZT will be equal to, yes, IZT into R delta Z plus L delta Z del Y del T I ZT and plus V Z plus delta Z T. So what will be VZT? VZT will be equal to, so you write here I okay, so IZT into R delta Z plus L delta Z del Y del T I Z plus V Z plus delta. So this is the Kirchhoff's voltage. This is Kirchhoff's voltage. So then what will be VZT minus, this is correct or not what I have written? VZT minus VZ plus Z plus delta ZT and divide Y delta Z is equal to
IZT plus IZT plus L into
IZT into R plus L del Y del T and I. Now apply Kirchhoff's current law. And no, first you and apply limit. Limit delta Z tends to 0. Limit delta Z tends to 0. Then it will be equal to minus del V upon del Z is equal to limit delta Z tends to 0. So minus del V by del Z will be equal to here IR plus L I by L T. Here you can write ZT, here also ZT and Z. So basically this is a function of Z and T both. So you can write phasor current and phasor voltage. We can separate this time, but we have to assume harmonic time dependence. So phasor voltage and phasor current. In terms of that also we can write it. So now apply Kirchhoff's current law. Apply Kirchhoff's current law. See here it is written minus del V ZT del Z is equal to. Okay. So here it is written. Now apply Kirchhoff's current law. KCL. KVL is done, and this is the equation. Remember it. Minus del V by del Z is equal to IR plus L del I by del T. So now Kirchhoff's current law. So Kirchhoff's KCL. Use KCL. So as per KCL, figure is shown to you.
IZT equals to IZ plus delta Z plus delta I.
Yes. Yes. IZT is equal to delta I plus IZ plus delta Z, comma. Good. So basically the Kirchhoff's current law is simple. It is here IZT is equal to delta Z plus delta I. So delta I so delta I is plus I Z plus delta Z comma is equal to, so that is IZT is equal to I Z plus delta Z comma T plus, now what will be delta I? See again figure is shown to you. What will be delta I as per this figure? What will be delta I? G into delta Z into V Z plus delta Z comma T and T delta Z del Y del T of V Z plus delta Z comma T O. Same thing you write here. So G into delta Z into V plus P delta del upon del T V Z plus delta Z. So that is limit delta Z tends to 0 and IZ T minus I Z plus delta Z comma T divide by delta Z is equal to minus del I by del Z is equal to G V and G into V function of ZT plus P del V Y del. Is it okay or not? Is it okay for you? This one?
Yes, sir.
Sir, it should be G into V Z plus delta Z comma T, right?
That is correct. That is correct. So, but delta Z tends to 0, na? So, you are correct.
Okay.
It should be like this. But delta Z tends to 0. You apply limit in both sides. You have to apply limit. So that will be this system because delta Z tends to 0.
Okay, sir.
So this is KCL, and what was KVL? So KVL was, as per KVL, we had done minus del. What we had done? If you remember, minus del V ZT Y del Z is equal to I R into IZT plus L into del by del T I. So here this we have one equation from KVL. So the question is how to solve these two differentially, partial differences. So these are partial differences because del y del z. Okay, because they are function of both the time and z. So what to do? Assume harmonic time dependence. So assumption is harmonic time dependence e to the power j omega t, e to the power j omega. So voltage and current that we want to calculate. So they are following this harmonic time dependence. They are basically sinusoidal of sinusoidal oscillation. Sinusoidal current oscillation. So e to the power j omega. If you assume like this, then what will happen? Fourier series, you know what is Fourier series? Fourier transform, those things you know. So harmonic time dependence. So we can write in terms of sine and cos. So what will be then these equations? These two equations, if this is the assumption here for voltage and current. Harmonic time dependence e to the power j omega t. Then how we can write this equation in Phasor form? Yes, how we can write in Phasor form? So in Phasor form, then it will be only the function of z, only the function of z. So it will become ordinary differential, not partial. So, but for voltage and current, you have to use this notation. Phasor you want to write. So Vs for voltage in Phasor form. This is Phasor voltage and Is is Phasor current. You have to write like this. So minus dVs upon dz is equal to Ris plus L dis upon. So yeah, again del y del t. So in Phasor form, what will be that del y del t? Because in Phasor form, what will be that del y del t is equivalent to j omega. Is equivalent to j omega because you have assumed e to the power j omega t dependence. So j omega L into Is, it will be like that. See here. All these things we have done. Phasor dependence, we are doing harmonic time dependence. is here j omega is and into s r into s. So this will be ordinary differential equation. So Phasor dependence we have to assume. VZT is the real part of Phasor voltage into e to the power j omega. So real part of Phasor voltage to e to the power j omega. Similarly, IZT will be real part of ISZ into e to the power j omega. So then in terms of Phasor voltage and Phasor current, how we can write these two equations? How we can write? If VZT is equal to, if you put here real part of VSZ into e to the power j omega, you can put it here directly. In this equation also, IZT is equal to real part of IS e to the power j omega. So these two you have to put in these two equations. So what you will get then? So minus dVs upon dz is equal to RIS plus j omega L IS. So R plus j omega L I is equal to minus dVs by d. See here, R plus j omega L into IS is equal to minus dVs by d. And similarly here what will happen? Minus d IS by dz will be equal to G into Vs, Phasor voltage, plus del by del t, so j omega c Vs. So G plus j omega c into Vsj is equal to minus dis by dz. So this will be two equations for voltage and current in Phasor form. So basically minus dVs by dz is equal to R plus j omega L into IS, and minus dis by dz is equal to G plus j omega c into Vs. These two equations will be there. Minus dVs by dz is equal to R plus j omega L into IS, and minus dis upon dz is equal to G plus j omega c into V. Phasor current, Phasor voltage. So now the question is how to solve this equation. Yes, how to solve? How to solve these two equations? See, voltage and current are coupled here. Here voltage is in terms of current. Here current is in terms of voltage. We have to separate it out so that we can solve one equation to find voltage or current. So already you have done this double differentiation. Those things you have done. So finally you tell what will be voltage and current. Okay, what will be that equation if we again differentiate? Minus d square Vs upon dz square is equal to R plus j omega L dis upon dz. dis upon dz, which is equal to minus E plus j omega c into Vs. So minus minus will be cancelled. So this minus minus is gone. So basically we have now d square upon dz square Vsz is equal to R plus j omega L g plus into g plus j omega c. So the gamma square Vs. So how to solve this? How to solve? So d square upon dz square minus gamma square Vsz equal to g. So second order ODE, ordinary differential equation. How to solve this? What will be the solution? What will be the solution? All are silent. Yes, what will be the solution for Vsz? Yes, you tell what will be the solution. Vsz already you have done. For Vsz will be equal to V naught plus e to the power minus gamma z plus V naught minus e to the power gamma. It is similarly for current also. See, Vsz is equal to V naught plus e to the power minus gamma z. Okay, the same thing. What I have. So that will be the solution for this. You have done this thing. Okay, and for current, this is for voltage. For current, what will be the equation? Same equation, d square upon dz square minus gamma square into Isz is equal to 0. What will be current? Isz is equal to I naught plus e to the power minus gamma z. What will be current? The expression for current. So, and plus I naught minus e to the power gamma. So, this is traveling in the plus z direction, this wave is traveling in the minus z direction. Similarly, this phasor current wave is traveling in the plus z direction, this phasor current wave is traveling in the minus z direction. So that is indicated here. Traveling in the plus z, this is traveling in the minus z, this phasor current wave is traveling in the plus z, and this component, phasor current component, is traveling in the minus. Gamma is the propagation constant that you know. So gamma, you know, gamma square you wrote here. So this is basically gamma square, this much. So basically gamma will be equal to under root R plus j omega L into j omega C. This is equal to alpha plus j beta. Also you know this, all these things you know. So this is equal to alpha plus j. Alpha is the attenuation constant. It is in per meter. This is also in per meter. So this will be in Nepers per meter or in decibel per meter. 1 Neper is equal to 8.686 decibel is equal to 1 Neper. Okay, and beta will be the phase constant in radian per meter. Okay, good. So next, okay. So we just calculated phasor current and phasor voltage, VSZ and ISZ. What about the instantaneous current and voltage at any instant? So what will be that? What will be that? VZT is equal to real part of VSZ into, this is what you had done, na? This is what you had done. So now you calculate VSZ. So this VSZ you calculated, so VZT you want. Put it here. This VSZ, this you put it here. You will get VZT. Similarly, this ISZ, this thing, you put it and calculate IZT is equal to real part of ISZ e to the power j omega t. Put it here. You will get IZT also. So basically, what you will get is here after putting this one. V naught plus into e to the power minus alpha z cos omega t minus beta z plus V naught minus e to the power alpha z cos omega t plus beta z. This is the solution. This is the solution for VZT. This one. Did you get it or not? All are silent. This V naught plus e to the power minus alpha z cos omega t minus beta z plus V naught minus e to the power alpha z cos omega t plus beta z. This we have got by doing all this. Real part of this and real part of this. From phasor form to instantaneous current and voltage expression. Okay, instantaneous expression for voltage. Okay. So then, how we define characteristic impedance of a transmission line? How we define? So characteristic impedance of a transmission line is the ratio of V naught plus and I naught plus. V naught plus and I naught plus. So this is here V naught plus divided by I naught plus. The ratio of the positively traveling voltage wave to that of positively traveling current. So V naught plus divided by I naught plus. See, V naught plus divided by I naught plus. So these two equations, these two VSZ and ISZ that we have done, this VSZ and ISZ we have to put in differential equation. VSZ and ISZ. Which equation we have to put? We have to put VSZ and ISZ here. Minus DIS upon DZ is equal to G plus J omega C, and for VS you put it here. And similarly for IS, this is IS, so IS you put it here. And when you will do this, so basically what you will get in terms of I naught plus and I naught minus, V naught plus and V naught minus some relationship. So from that, it is written that Z naught plus is equal to V naught. This is basically, this much is the diffusion. V naught plus divided by I naught plus. And this will be equal to, if you do that, if you do this, so that will be equal to V naught, Z naught is equal to V naught plus divided by I naught plus is equal to minus V naught minus divided by I naught minus. That will be equal to R plus J omega L divided by omega, which will be equal to with this gamma divided by G plus J omega C. So basically Z naught will be equal to this thing. And how we have got this? You have to put ISZ and VSZ in these two equations. And propagation constant that is gamma, and the characteristic impedance is the ratio of V naught plus and I naught plus, positively traveling voltage wave to the positively traveling current. That is the characteristic impedance. Okay, so Z naught will be basically gamma. You put it here, you know what is gamma under root R plus J omega L and G plus J omega C. So that will be basically this thing. This also you know Z naught. And okay, so in the next class I will discuss lossless line and distortionless line. Okay, for lossless line, lossy transmission line that we were discussing. After that we will discuss lossless transmission line and distortionless, and the general case already we have done gamma and the Z naught for the general case. Okay. So now I will stop the recording. If you have any question, you can ask. Okay, and video recording I will also share.
Thank you, sir.